Hey guys, I'm Mr. C. Welcome to our lesson on right triangle trigonometry. So here's your warm-up, right? At the Pythagorean theorem, right? Now, the reason why we warmed up with the Pythagorean theorem is because I want you to understand that all right triangle trigonometry is part of something that you've been doing since, I don't know, at least middle school, right? When you learn the Pythagorean theorem, we're dealing with right triangles, right? So we're going to talk about all sorts of right triangle problems. I want you to understand all right triangle trigonometry problems are one type of right triangle problem. So here, I mean, you guys were all pretty quick to say, oh, hey, we got if we call this A, right, we call this B, we call this C, right, you got A squared plus B squared equals C squared, right? A is the mystery. I don't know, maybe I should just leave it as A instead of making it X, but whatever. B is 17 and C is 19, right? And then you got your calculator, right? So X squared plus 17 times 17 or 17 squared is 289. Big numbers, but I'm not scared because I got a calculator. 19 times 19 times 19 is 361. All right, subtract 289 from both sides. 72. Okay, so x squared is 72. So what is x? It will be the square root of 72. Now, I think what I need to do here is take this as an opportunity to review simplifying radicals, really, because I know the Pythagorean theorem was no big shakes for you guys, but simplifying radicals may have been. So anyway, so let's do this. So sure, you could say that the square root of 72, you could say that is approximately, well, it's got to be between the square root of 64, which is 8, and the square root of 81, which is 9, right? So you could look at it and say, you know, maybe it's a little closer to 72. I don't know if it really is, but actually, no, I don't think. Let's see. So it's 8 away from that. 9, oh yeah, okay. So you might say, hey, it's 8.5, right? Sure, approximately 8.5, right? All right, that would have gotten you through most middle school math classes, maybe even your high school geometry class. But the skill that they're going to want you to be able to do, especially as you guys are taking Algebra 2, and as you guys are taking the MCAS and the SATs, is to simplify these radicals, right? So 72, what I'm looking for is to make the number underneath the radical as small as possible, right? I could break this down as square root of 36 times the square root of 2. Why the square root of 36? Why did I factor that out? Because that could be simplified as 6. So this would actually be the answer in simplified radical form. As you guys get to higher and higher levels of mathematics, you are going to be expected to write your answers in simplified radical form. So anyway, that's why I did that. Okay, so next one. We got our A, we got our B. A and B are interchangeable, by the way, as many of you know. But the one that is not interchangeable, the one that is not interchangeable is C, right? Is always going to be the hypotenuse, always going to be the longest side, always going to be the side opposite that right angle. Right? Okay. This one, some of you guys thought was a little more straightforward because you're trying to solve for C, which is what you guys always had to solve for in those problems when you first learned the Pythagorean theorem, right? So 5 squared plus 13 squared equals C squared. I'll just leave it as C. Okay, so we get 25 plus. I think this is 169, but let me make sure. When you got a calculator by your side, there is no excuse for making mistakes like that. I add the two together. So 194. Okay, and again, I know I could say that C is going to be the square root of 194. And I'm going to do the same exact exercise over here. So the square root of 194, right? 194. This is a little harder because typically people don't know square roots above, you know, like square root of 144 usually. Okay, so what is so just to be clear, so let's see. So so the square root of so square root of 169, as we just established, is 13, right? 14 squared, and all I'm doing is squaring things, right? Is 196. Okay. I don't know why my tablet's lagging a little here, right? But so what I would do if I was going to estimate this, I'd say 13.9. Or you might even say, like, you might even say 14.0. You might say that 14. But anyway, that's not simple. That is not in simplified radical form. Now, this is a kind of thing where if you want to find this in simplified radical form, you might have to do a little math, right? So what I'm going to do is I'm going to take my perfect squares. Now, the perfect squares, you know, what are they, right? There's the square root of 4, the square root of 9, the square root of 25. Hope my face isn't blocking this. And I'm going to just see, like, can I divide out any of these? So 194 divided by 4. Let's see what happens. Nope. 194 divided by 9. Let's see. Nope. Okay, let's just kind of keep going up the ladder. Oh, did I forget 16? My bad. I forgot the square root of 16. But you know what? That is not going to work because 4 didn't work, right? So, okay, and I guess we could keep going up here. 36 won't work because 4 and 9 didn't work, right? So I'm going to cross that off, right? 49, maybe 49 works. Let's see. 194. Nope. All right. Anyway, I'm kind of running out of options here. 70. Let's see, what's next? 64. 194 divided by 64. Nope. 194 divided by 81. Nope. And so you may find out that actually this is already in simplified radical form, which, hey, it wasn't too exciting, but anyway. So that is what it is, you know, whether you write 13.9 or the square root of 194, either way, that works. Anyway, and hey, if this was super review for you, hopefully you fast forwarded through the video. But those of you that it wasn't review for, I hope that you enjoyed this. Okay, so again, Pythagorean theorem, a squared plus b squared equals c squared, right? Hey, I basically said all I have to say about that, right? The big thing here is just recognizing that c squared, right, it's going to be the hypotenuse that's on the side by itself, right? You're not always solving for the hypotenuse like you saw in our first problem. Sometimes you're solving for one of these sides. A and B are interchangeable for the purpose of the Pythagorean theorem. So if this was B, right, and that was A, that's totally cool. Okay, and this is where, you know, IXL preview, and again, this is very similar to what you guys did for the warm-up, so I don't want to belabor this, but let's say we call this A, we call this B, we call this C, right? What's the length of the missing side, right? You got your A squared plus B squared equals C squared, right? All you're doing is just trading numbers for letters here. Right? See how the themes keep coming back, you guys, trading numbers for letters? And I think I can actually do this in my head, right? You got that's plus 36 equals 81, right? Subtract 36 from both sides. I don't know. I'm not proud. I'm going to use my calculator here. Minus 36. 45. Not because I couldn't do it. It was because, you know, I want to make sure it's right, which I guess means I couldn't do it. But anyway, making extra sure that I'm right. Okay, so now again, A, right, is going to be the square root of 45. Remember, we undo square by square rooting, right? Is this simplified radical form? I mean, sure, you could say that this has to be between the square root of 36 and the square root of 49, right? So you could look at it and say, oh, it's going to be, right, 6.5 I don't know, maybe it's a little close, 6.7 or 6.8 maybe. Sure, you could do that, right? But for the purpose of your higher level math classes, they're gonna want you to throw this in simplified radical form. So what I can do is I could break this down as the square root of 9 times the square root of 5. Why did I factor the square root of 9, that perfect square? Because I can make it a whole number, make it 3, and there you have it. That is actually the legit answer there that you're gonna be expected to deliver for your higher level math classes and probably for the MCAS. All right, also in IXL, you will be given word problems, right? My suggestion when you have a word problem like this is draw the picture. He walks 4.2 feet from the edge of the slide back to the ladder, okay, and then he climbs 7.5 feet to the top of the slide again. How long is the slide? If necessary, round to the nearest tenth. It should be how long is the slide? How about that? A typo in IXL. All right, but anyway, so what do we got? We've got from the end of the slide to the ladder. So what we've got here is I'm imagining the ladder is straight up and down as ladders tend to be, right? This is the slide, right? So just to be, so this is your slide. This is your ladder. Okay, and this is just kind of the other part of the piece of the triangle, other side of the triangle. Now, what represents what? So, so let's see, he walks 4.2 feet from the end of the slide back to the ladder. Oh, from here to here is 4.2 feet. Okay, and then he climbs 7.5 feet to the top of the slide. Okay, so he's climbing the ladder, which I guess is what you would climb, right? Even though some troublemakers might try to climb up the slide, that's not safe. Okay, so now I've got my a squared plus b squared equals c squared. And of course, I'm talking in a community playground, you know, whatever you guys want to do in the comfort of your own backyard, you know, you do. But yeah, community playground, climbing up the slide, way out of bounds. Okay, so here we go. Okay, so what we've got is we've got 4.2 squared plus 7.5 squared equals c squared. Anyway, at this point, I think you guys know how to solve it, right? You know, 17.64. But you know what? I guess if you know how to solve it, you're probably fast forwarding the video anyway. So, hey, my conscience is clear. 7.5 times 7.5. All right, 56.25. Yeah, that's right. I'm going 2 decimal places. Okay, so add those two together. 73.89, right? Okay. Okay, and I guess, I mean, the truth is here, I guess you're looking for a decimal approximation here. I mean, we're not going to get this thing in simplified radical form, obviously, right? I don't know how you would get a decimal in simplified radical form. Some of you guys, some of you high-end math students might have an idea how to do that. I don't know. Okay. Okay, hold on. We 73.89. Okay, so C is going to be, I guess I'll go 2 decimal places. I've been doing that the whole time. 8.595. So actually 8.60 feet. All right, cool. And it makes sense. Again, always, does it make sense, right? So the slide is going to be longer than either of these two sides, obviously, because it's the hypotenuse, right? And so it makes sense that that would be 8.6 feet, more than both the ladder and the distance from the slide to the ladder. All right, now, special right triangles. Okay, so so again, these are, I'll just do some real simple examples here. These are the 2 common ones. Again, special right triangles come up all the time. And usually it's not, hey, solve for this side of a special right triangle. Usually, you know, if you're trying to find like the area of kind of a more complex figure, you know, being able to find the, you know, recognize a special right triangle within a bigger shape is typically how these things come up on the MCAS and these advanced problems. So basically, how would this be? Well, just imagine with our 45, 45, this is 5, right? Also called an isosceles right triangle. This would have to be 5, and this would be 5 times the square root of 2, right? Whatever that is, right? Like maybe 7 something. Here, right? If let's say this side was just 5 centimeters, right? This would be, the long side would be double that, right? So it'd be 10, and this would be 5 times the square root of 3. Of course, important to recognize this is the 30, and this is the 60. Right? Whereas here, both of these base angles always be 45 if it is an isosceles right triangle. Okay, so anyway, that's a quick review of what that is. I mean, many times you have, you're given like the long side or the hypotenuse, you have to find one of the other sides. Slightly more challenging problem. But hey, let's see what IXL has for us. Find T. Okay, so again, right, our ratio, right? So again, if this is X, right, what do we do to get to here? We just multiply by the square root of 2, right? So 3 times the square root of 2 times the square root of 2, right, actually ends up being 3 times 2, which is 6. Well, the answer there is 6. Right? And by the way, if they gave you T and you had to find one of the other sides, you would just divide by the square root of 2. You would just do the opposite. Okay, now here, finding T, right? So this one here, right? This is the long side. This is the short side, right? So what this is going to be half of that, which is just going to be 1 times the square root of 3. Okay, and then what they're not asking you here is this, but if they did, right, it would be the square root of 3 times the square root of 3, which is just 3. If they were asking for that side, which they weren't, square root of 3 is the correct answer. All right, that was a slightly more challenging problem in my opinion because they're giving you the hypotenuse and you have to find, one of the other side. Maybe it wasn't that much harder. Okay, and that's what you will see on IXL. Okay, now for the moneymaker, the thing that students tend to freak out about. Don't freak out, right? Just right triangle trigonometry, SOHCAHTOA. What the heck does SOHCAHTOA mean, right? SOHCAHTOA. I don't know why that's easy to remember, but it is, right? The sine is equal to the opposite over the hypotenuse. The cosine is equal to the adjacent over the hypotenuse, and the tangent is the opposite over the adjacent. So with respect to this angle here, right, they showed you the ratios here, right? This is the opposite, which is kind of obvious because it's opposite that angle, right? Adjacent is just fancy for next to, right? And then the hypotenuse will never change. The hypotenuse is always the one opposite the right angle. Whereas depending on the angle you're talking about, the opposite and adjacent may flip-flop. Okay, so now let's see some problems here. So what do we got? Before we see some problems, again, all of this is kind of the family of right triangles, right? So what I kind of say, hey, plan A, if you can solve using the Pythagorean theorem, I mean, I guess you could say this could be your plan A too, but this is kind of like a special case. And also with special right triangles, if you only have one side, right? Here, Pythagorean theorem, you need 2 sides, right? Special right triangles, you got one side, you can figure out everything else, right? So anyway, then trig is like, well, we're going to see reasons why we will use this to solve problems. But if you think of this as kind of plan A, plan B, and plan C, that might be helpful to you. Okay, so right triangle trig. What kind of questions are we going to be asked for? Wow, well, I picked this problem because they're asking me to kind of run the table, right? The sine, cosine, and tangent of angle A. So this angle right here. Okay, so what do we got here? So we've got the opposite, we've got the adjacent, and we got the hypotenuse. Okay, so let's start. Well, first of all, all right, let's start with sine since it's the first one listed, right? So we know that it's going to be opposite over hypotenuse. The thing is, what is this, right? So I really wanted you to see this problem because there are limits to right triangle trigonometry, right? Because the thing is, in order to do this problem, in order to figure out the ratio of the opposite over the hypotenuse, you got to figure out what the opposite is, right? So how do you do that? How do you do that? You do that with that basic, right? The first thing we did today, right? The Pythagorean theorem, right? So think of these things, the Pythagorean theorem, right triangle trigonometry, as working together, not as a squared plus b, the Pythagorean theorem, something that you learned in 7th grade and you're never going to have to think about, right? And right triangle trig is something advanced that you hotshot 10th graders are doing, right? No, that's not what it is. It's all part of the same puzzle, right? So you need to think of it that way, right? So let's just say I'll call this x for now. All right, so here, let's see, if I call this, okay, a squared, so the square root of 26 squared, right, plus x squared, and again, these could have been interchangeable, equals 3 times the square root of 5 squared, right? Okay, so square root of 26 squared actually is much easier than think. It's actually 26. Right? The square root of anything squared is just going to be that number. Okay, now 3 times the square root of 5. This is a little tricky because what you've got is you're squaring 3, which is 9, and the square root of 5, which is 5, right? 9 times 5 is 45. Now, if you typed it in your calculator, right, in parentheses, right, you would get 45. Of course, you get a decimal approximation, it would have to be exactly the square root of 5 in order to make that work. Now, x squared equals, okay, so 45 minus 26, I believe, is 19, right? And so x is the square root of 19. Okay, now, okay, for the purpose of this problem, okay, so the sign opposite, so this is the square root of 19, right? Right. So this is the square root of 19 over the square root of, I'm going to call it the square root of 45, right? Okay. I know that's not in simplified radical form, but I'm just going to keep it simple. The cosine is the adjacent, the square root of 26 over the square root of 45, right? And then this is opposite over adjacent, the square root of 19 over square root of 26. Now, they say that they want this simplified and rationalized. Okay. All right. So what that means, everything needs to be in simplified radical form, and we can have no radicals in the denominator. Okay. So we're going kind of, into the rabbit hole here of what the heck, how do we make it simplified and rationalized? So this is going further and deeper than just basic right triangle trigonometry, right? So anyway, let's talk about that. How do we rationalize the denominator, right? So, okay, I'm going to call this, I shouldn't have called it the square root of 45. I should have called it 3 times the square root of 5. But anyway, so here we've got, over here, square root of 19 over 3 times the square root of 5. How do I rationalize this? Now, general rule when you're rationalizing things, right? The mathematicians hate weird stuff in the denominator. Right? They don't like weird things going in the denominator. What the heck am I talking about, right? Weird things are like 0 and radicals. Okay, so we got to figure out how to get rid of this square root of 5. So what I'm going to do is I'm going to multiply the top and the bottom by the square root of 5, right? And what that will do is my denominator becomes 3 times square root of 5 times square root of 5, which is 5, right? My numerator, I can just multiply what's underneath these radicals. I think I believe it's the square root of 95, right? So what I have now, if I have rationalized the denominator, is the square root of 95, right, over 15. Okay, it is rationalized. Thing I don't know, is it also simplified, right? And in order to simplify it, what I got to do is I got to simplify that radical of the square root of 95, right? And I have to look at all of my perfect squares. So I've got, actually I won't write this, I'll just write all those perfect squares. We got 4, we got 9, we got 16, we've got 25, we've got 36, we've got 49, and I could go on, but it's any of these going to be factors of 95, right? So I always start from the biggest one, right? 95 divided by 49, nope, that's not a whole number. 95 divided by 36, nope, that will not be a whole number. 95 divided by 25, nope, will not be a whole number. I don't think, nope, because it would be 75 or 100. 95 divided by 16, I don't think so. Anyway, if you really want to try, give it, type in your calculator, 95 divided by 16. No, that's not a whole number. 95 divided by 9, I don't think so. But you know what? Why not? Give it a shot. Nope. 95 divided by 4, nope, because it would have been an even number. So truth be told, this is rationalized and simplified. I know that was a lot right there, right? But that's what we're talking about, where we are simplifying the denominator. Excuse me, simplifying and rationalizing. Now, same thing here, right? I guess we're just going to continue. Yeah, what the heck? You guys, if you don't like it, you would have fast forwarded the video by now. So what I'm going to do is I get the square root of 26 times 3 times the square root of 5, which I should have simplified before. I shouldn't have written it as square root of 45, but hope you guys forgive me for that. I'm going to do the exact same thing, multiply the numerator and denominator by the square root of 5. No surprises, my denominator will once again be 15. And my numerator will be, let's see, 26 times 5, the square root of 130. Now, the million-dollar question here, can 130, is the square root of 130 in simplified radical form? Now, I don't know. I may even have to go up a little more. 81, 100. All right. Can any of these 130 be divided by any of these? Well, I can pretty much knock off the top 3. 36, I don't think so. But what the heck? I'll just give it a shot. 130 divided by 36. Nope. Definitely not 25, because 125 would have been a factor. 16, I don't think so. I do not think so. But what the heck? I'll give it a shot. Nope. And then 9. Ooh, I don't know. Okay, 130. Actually, it would not be, because 130 is not even a factor of 3, let alone 9. All right, and then finally 130 divided by 4. We might get this one. No, not even 4, right? So again, simplified radical form once again, right? And I know this is, some of you are like, yeah, Mr. C, I get it. Hopefully those of you guys that are there have already fast forwarded through this. Okay, so this is, we might end up with some crazy numbers here if we're really trying to simplify this denominator. But the only thing I can think to multiply this by, since that is in simplified radical form, is actually the square root of 26. Which makes the denominator look great, right? Because we just got nice, clean, whole number of 26, right? Nice, easy, whole number, not 25, 26, right? But the numerator is gonna get sloppy. Now the thing is, lucky for us, you can get as sloppy as you wanna get on that numerator. Nobody cares, right? So the square root of 494, right? All right, if I really wanna simplify this, man, IXL, man, they're really busting our chops, making us simplify and rationalize, right? But hey, I'm not complaining. Okay, now maybe I should go higher than this, but I'm not gonna for now, right? If it turns out, I may have to simplify a couple of times, but anyway, here, square root of 494. We may actually find out what we found out in the previous 2 examples, that this actually can't be simplified. But anyway, square root of 494, let's see, divided by 81. Nope. Okay, 494 divided by 49. Nope. 494, definitely not 25. 494 divided by 16. Nope. 494, it's not going to be 9, because those digits would have to divide by 9. 494, we're even going to get 4? No, not even 4. Okay, hey, simplified radical form once again anyway. Man, IXL really busted our chops with this simplified radical form. I don't know. Maybe I made an arithmetic mistake somewhere in here, and these problems shook out a little simpler than they seem, but it doesn't look like it from where I'm standing. Anyway, take that for what it is. I picked that because it was kind of a problem with a lot of action, and yeah, it was. 20 minutes later, yeah, we're still doing it. Yeah, it was. Okay, so right triangle trig here. Again, remember the ratios. We have similar triangles, so this is kind of the relationship between similar triangles and SOHCAHTOA. And if we want to know the tangent of D, right, because you have similar triangles, right, D is going to be the same angle as E, right? It is, because they are similar triangles, right? These are parallel lines, right? These, anyway, basic review of those corresponding angles. All right, so anyway, the tangent, right? We've got the opposite, we've got the adjacent, and we've got the hypotenuse, right? So the opposite over adjacent, it is going to be, and just where does this come from? Tangent is opposite over adjacent, right? Which is 16 over 30, which can be reduced. Oh, isn't it nice to have nice whole numbers like this instead of the square root of 19 and all that weird stuff? Let's see. So if I divide both of these by 2, I get 8 over 15. Yeah, I think that's what we got, 8 over 15. I think that's as simple as you can make it. All right, so there's right triangle trigonometry with similar triangles, right, from the last lesson or 2 lessons ago, kind of going hand in hand. Okay, here we go. Okay, this is where you actually have to solve for missing sides. So x, y, right here, I guess I'll call that, I'll just call that side W, right? Why not? So here, we know we got an angle, right? And I guess we could figure out that angle too, but this is the one they're giving us, right? And we also know that we have the SOHCAHTOA relationship. So opposite, adjacent, and hypotenuse. Now, what one has O and A? Let's see, SOHCAHTOA. It is the tangent. The tangent is the opposite over the adjacent, right? So what does that mean in this case? All right, the tangent of 31 degrees is equal to the opposite, which is 4, over the adjacent, which is W. Okay, tangent of 31. Students freak out. What the heck is that? How am I supposed to know that? Well, you don't need to know. The truth is your calculator does. I'm just typing in tan 31, and here I got a number, which happens to be 0.601. I always go 3 decimal places. Now, what do you do when you have a variable denominator? I don't like it any more than you guys, you know. I know that's just some shortcuts. I'm going to multiply both sides by W. So 0.601 W equals 4. Divide both sides by 0.601. When in doubt, I always do all the algebra, right? So W is going to equal 4 divided by 0.601. And there we have it, 6. W equals 6.66 actually, if we go too deep. Okay. So there we have it, right? And it makes sense, right? If this is 31 degrees, this would be like 59 degrees. So it makes sense that this side would be a little bigger than that side, and it is, right? So, anyway, that's that. Here is an actual MCAS problem that is asking us to apply what we know about right triangle trig, right? What is the sign in terms of the sides of EFG? Write your response and the answer provided. So the sign of this, right? You get the opposite over the hypotenuse, right? So it is going to be, so just to be clear, the sign of this angle is going to be the opposite, which is FG. It's the opposite over the hypotenuse, which is EG. Is that an answer choice for us? FG, oh yeah, B, there we go. Okay, that wasn't so bad. But this is, I think this is a multi-part one, so that was the easiest. Let's see what we're getting at next. What is the relationship between the sine of this angle? Okay, so sine and the cos. Oh, okay. So first of all right, what do I want to? Can I just call this? Let me just call this A, B, C. Let me do that. Right? Let me just label those. I know you say, hey, this is FE, this is FG, this is EG. Why don't you call them their appropriate names? I'm just trying to keep this simple here, right? So the sine of this angle, right? So the sine, right, in this case is the opposite over the hypotenuse, right? And this would be the adjacent, right? So this is going to be, I guess, B over C, right? All right. Now the cosine. Now we're talking about angle G, right? Now we're talking about angle G. Sure, the hypotenuse stays the same. That is true, right? But the opposite and adjacent sides are flip-flopped, right? So the cosine of angle G, right, is going to be adjacent over the hypotenuse, and so that's going to be B over C. So what do we know about these? They are the same thing. And this is something that comes up time and time and time again. The sine of angles that are complementary to each other are going to be the same. The sine of an angle and the cosine of the angle complementary to it are going to be the same because of this SOHCAHTOA relationship. So that is something that if you remember that, great. And if you have to work through a little SOHCAHTOA diagram every time you get one of these problems, hey, that's fine too. Okay, so now, oh, this is looking pretty wild. If the sine of 30 degrees is 1/2 and the cosine of a mystery angle is 1/2, right? What is the value of this in degrees? Now, all right, so hey, if this is the sine of 30 degrees and the cosine, these are the same thing, right? They equal each other, right? This is piggybacking off the same problem, right? If the sine of one angle and the cosine of another angle equal each other, it means that these two angles have to add up to 90 degrees, right? They have to be complementary, right? So, hey, if this is 30, right, and this is our mystery angle, it has to be 60, right? So again, right, anyway, what the heck, I'll talk it through. You guys have watched this far in the video, you appreciate me talking it through. So anyway, if the sine of 30 degrees is 1/2, right, so the opposite over the hypotenuse, right, has the ratio of 1 to 2, right? Oh, I'm sorry, the sine, this would be 1 because this is opposite, right? This 30-degree angle is 1 to 2, right? When we start talking about this angle, all of a sudden this becomes the adjacent, right? So that's why that rule is what it is. Anyway, so if you remember the rule that these angles have to add up to 90, they have to be complementary, great. If you had to work through a SOHCAHTOA diagram, that's great too. Okay, now consider this complete equation. The cosine of G is going to equal cosine of something. Complete the equation so that the cosine of G in terms of theta. Okay, this is basically the exact same problem we have seen again and again and again, right? So if this is mystery angle, right, we know this has to be 90 minus that mystery angle. Okay, right? So, right, since we're saying G, angle G, another name for angle G is 90 minus beta. So, hey, we're just explaining the same thing. Basically, these problems are asking you to do the same problem pretty much in 3 different ways or 3 different times, right? Whether you sketch out a SOHCAHTOA diagram or you just remember this rule. Either way, it makes a ton of sense. And another way to think of this, if the triangle, all the angles have to add up to 180, right? If you think about that, this has to be 90, right? So if these have to add up to 180, right? These two have to add up to 90. Anyway, hope that helps. Hope that's a benefit to you. Hey, that's it, you guys. Again, I'm Mr. C. Hope you enjoyed this lesson, and I'm going to look forward to seeing you guys in class.